High-Speed Packet Access or HSPA is an amalgamation of two mobile telephony protocols, High-Speed Downlink Packet Access or HSDPA and High-Speed Uplink Packet Access or HSUPA, that extends and improves the performance of existing third-generation mobile telecommunication networks utilizing the WCDMA protocols. The first step required to upgrade WCDMA to HSPA is to improve the downlink by introducing HSDPA. It is defined in UMTS Release 5 or R5 specifications. The second step is to upgrade the uplink by introducing HSUPA, which is introduced in 3GPP Release 6. After completing this section, you will be able to understand new features introduced in UMTS Release 5 and Release 6. Explain the evolution of IMS. Elaborate the network architecture of IMS and how it interfaces with Packet Core Network. Explain the advantages of HSPA. Define the network evolution from UMTS Release 99 for both HSDPA and HSUPA. Explain the key technology enhancements over air interface for both HSDPA and HSUPA. Through Release 99 or R99, the 5 MHz UMTS carrier was defined to provide capacity and user performance advantages over predecessor technologies such as GSM, GPRS and Edge. Release 5 or R5 specifications, which extends the R99 and R4 specifications, is a crucial step towards the development and implementation of services in the mobile environment. R5 introduced 3 major enhancements. First, at the network level, Release 5 introduces IP Multimedia Subsystem or IMS. It brings to the operators the means to is the introduction of new multimedia services and applications. IMS is a subsystem that controls the provision of services between the servers and the core network. It allows integration of real-time applications and services. Second, R5 introduces High-Speed Downlink Packet Access, HSDPA. HSDPA technique allows a significant increase of the bit rates, as it becomes possible to reach several bits/second, up to 14, on the downlink channel. Services such as real-time video, web access, and FTP, etc. will receive improved throughputs and, thus, the end user perceives quality of service. HSDPA is mainly achieved by modifications in the radio subsystem. Finally, UMTS R5 introduces IP in the radio subsystem, IP-UTRAN, which generalizes the use of IP in the whole network comprising of UTRAN and core network. Let us now discuss each of these evolutions in more details. On the network side, the most important evolution in UMTS R5 is the introduction of IP Multimedia Subsystem, IMS. It provides a flexible architecture for the rapid deployment of innovative and sophisticated features. The IMS focuses on introducing both a technical and commercial framework for a mobile operator to offer person-to-person services using a wide range of integrated media, voice, text, picture, video, etc. The IMS standards have recommended the adoption of the Session Initiation Protocol, SIP, as the Service Control Protocol. IMS define an IP Multimedia Overlay Network, over UMTS and GPRS, for session control based on Internet protocols. The data or media transport, as well as signaling transport, happens via the underlying technology, for example, UMTS or GPRS. IMS effectively provides control mechanism, QoS, security, charging, using SIP for IP services, and person-to-person communication. As depicted in the figure, the IP Multimedia Core Network Subsystem is a collection of different functions linked by standardized interfaces, which are grouped to form one IMS administrative network. A function is not a node. An implementer is free to combine two functions in one node, or to split a single function into two or more nodes. Each node can also be present multiple times in a single network, for dimensioning, load balancing, or organizational issues. Let us look into the functionality of various IMS components. The Home Subscriber Server, HSS, is a master user database that supports the IMS network entities that actually handle calls. It contains the subscription-related information, performs authentication and authorization of the user, and can provide information about the subscriber's location and IP information. It is similar to the GSM Home Location Register, HLR, and Authentication Center, AUC. A subscriber location function, SLF, is needed to map user addresses when multiple HSS are used. Call Session Control Function, CSCF, provides the registration of the endpoints and routing of the SIP signaling messages to the appropriate application server. The CSCF works with the interworking and transport layer to guarantee QoS across all services. There are a number of roles defined for CSCF servers, including the following. Serving, SCSCF. This is a session control entity for endpoint devices that maintain session state. Proxy, PCSCF. This is the entry point to IMS for devices. Whether in a home network or visited network, the PCSCF will be the first point of contact for the UE and forward SIP messages to the user's home SCSCF. Interrogating, ICSCF. This entity within the IMS CSCF is a session control entity for endpoint devices that maintain session state. This is the entry point to IMS from other networks. A PSTN gateway interfaces with PSTN circuit switched networks. For signaling, CS networks use ISDN user part, ISUP, over message transfer part, MTP, while IMS uses SIP over IP. For media, CS networks use pulse code modulation, PCM, while IMS uses real-time transport protocol, RTP. IMS network introduces two gateways to perform these conversions. A media gateway, MGW, interfaces with the media plane of the CS network by converting between RTP and PCM. IMS, MGW supports media conversion, bearer control, and payload processing, for example codec, echo canceller, conference bridge. It interacts with the MGCF for resource control. A signaling gateway, SGW, interfaces with the signaling plane of the CS network. It transforms lower layer protocols, as string control transmission protocol, SCTP, an IP protocol, into message transfer part, MTP, and Signaling System 7, SS7, protocol, to pass ISDN user part, ISUP, from the MGCF to the CS network. A Media Gateway Controller function, MGCF, is a gateway between PSTN and IMS network. It is SIP endpoint that does call control protocol conversion between SIP and ISUP and interfaces with the SGW over SCTP. It also controls the resources in a media gateway, MGW, across H.248 interface. It communicates with CSCF and selects the CSCF depending on the routing number for incoming calls from legacy networks. Breakout Gateway Control Function, BGCF, selects the network in which a PSTN breakout is to occur. If the breakout is to occur in the same network as the BGCF, then the BGCF selects a Media Gateway Control Function, MGCF. This will be responsible for interworking with the PSTN. The MGCF then receives the SIP signaling from the BGCF. But in case the breakout has to happen on another network, then the BGCF selects a breakout that is to another network. In this case, the BGCF hands control of the session to the BGCF in the selected network. The Media Resource Function, MRF, provides media-related functions such as media manipulation, for example voice stream mixing, in playing of tones and announcements. Each MRF is further divided into a Media Resource Function Controller, MRFC, and a Media Resource Function Processor, MRFP. MRFC controls the media stream resources in the MRFP and interprets information coming from an application server and SCSCF. The MRFP is a media plane node used to mix, source or process media streams. It can also manage access right to shared resources. In 3GPP-R5, the GE-RAN is connected to the CN with IU interface. Interface IU, CS is defined for circuit switch data and IU, PS is defined for packet switch data. With IMS, the circuit switch domain will not be needed anymore. In CN, traffic from GE-RAN gets the same treatment as the traffic from the UTRAN, and the communication between access network and core network, both CS and PS, shall take place over the IPATM. Main differences between Release 99/Release 4 and R5 is that CS can quit service in R5, and the whole network will finally transfer to all IP. WCDMA is evolving to enable higher bit rates and throughput. The first step is to improve the downlink by introducing high-speed downlink packet access, HSDPA. The second step is to improve the uplink by introducing enhanced uplink. Together, these two technologies are known as high-speed packet access, HSPA. HSPA capabilities will benefit operators by providing higher performance and introducing new multimedia and streaming services. Also, operator will be able to increase the revenue through higher capacity, providing up to 5 times more system capacity in the downlink, and up to twice as much system capacity in the uplink, while reducing the production cost per bit. HSPA truly makes mobile and wireless broadband a reality. Advantages for operator in turn results in improved end-user experience through increased peak data rates to 14 megabit per second the downlink, and 5.8 megabit per second the uplink. Reduced latency. Let us now look into the evolution of HSDPA and HSUPA from UMTS Release 99. HSDPA upgrade of UMTS is similar to Edge upgrade of GPRS. Key attributes of HSDPA upgrader. HSDPA is completely backwards compatible. HSDPA works on 5 MHz spectrum, and there is no need for new spectrum. Reuse existing infrastructure with minor software and hardware upgrade in access network, thus making the migration from R99 UMTS to HSDPA very cost-effective. HSDPA is based on a new distributed architecture, enabling low delay link adaptation, channel quality feedback, and HARQ processing. This is accomplished by incorporating many of the key scheduling and control processes at the base station, as opposed to the radio network controller, RNC, and thus closer to the air interface. Specifically, the medium access control, MAC, functionality, which fully resided in the RNC in R99, is split between the RNC and Node B in REL 5. In REL 5, most of the key MAC functions, critical to delay and performance, are defined by the MAC HS, which is located in the Node B. In Release 5, HSDPA introduces a new transport layer channel, high-speed downlink shared channel, HSDSCH. It is implemented by introducing 3 new physical layer channels, HSPDSCH, HSSCCH and HSDPCCH. High-speed physical downlink shared channel, HSPDSCH, is a new downlink physical channel, which allows several users to share the air interface channel dynamically with peak channel rates up to 14 Mbps. HSPDSCH is mapped to the HSDSCH transport channel that carries actual user data. The HSPDSCH uses 2 millisecond transmission time intervals or TTI and a fixed spreading factor of 16 that allows for a maximum of 15 parallel codes for user traffic and signaling. High-speed shared control channel, HSSCCH, is HSDPA downlink control channel that informs all the UEs on how to decode the HSPDSCH, for example modulation, codes, retransmission information, etc. High-speed dedicated physical control channel, HSDPCCH, is uplink control channel defined to transfer fast channel quality indications, CQI, and ACNAC signaling for HARQ from the UE to Node B. The Node B gathers and utilizes the CQI of each active user to determine how much data to send to the user devices on the next transmission when that user is scheduled on the HSDSCH. It is transmitted with a fixed spreading factor of 256. HSDPA takes WCDMA to its fullest potential for providing broadband services, and is the highest throughput cellular data capability defined. HSDPA achieves its performance gains by upgrading various radio features of UMTS Release 99. Some of the major enhancements are: HSDPA uses both the modulation used in WCDMA, namely quadrature phase shift keying, QPSK, and under good radio conditions, an advanced modulation scheme, 16 quadrature amplitude modulation, 16 QAM. The benefit of 16 QAM is that 4 bits of data are transmitted in each radio symbol as opposed to 2 with QPSK. 16 QAM increases data throughput, while QPSK is available under adverse conditions. While R99 uses scheduling of packet data at the radio network controller (RNC) level, HSDPA moves these decisions to the base station, and thus closer to the air interface. HSDPA uses terminal feedback information about channel quality, terminal capabilities, quality of service, QoS, needs, and air interface resource availability to achieve more efficient scheduling of data packet transmissions. The fast scheduling capability of HSDPA can be taken advantage of through adaptive modulation and coding to provide all users the highest possible data rate. The modulation and coding schemes are adapted dynamically based on the quality of the radio link while maintaining the power level constant. Fast retransmissions and HARQ. When channel decoding of a data packet fails, due to interference or other causes, a mobile terminal immediately requests the retransmission of the data packets. While R99-based networks handle those retransmission requests by the RNC, in HSDPA those retransmission requests are managed in the base station. If decoding of the initial transmission fails, a retransmission is sent which is self-decodable or can be combined with the initial transmission, still kept in the buffer, before channel decoding. This operation is known as Hybrid Automatic Repeat Request, HARQ. User transmissions are assigned to one or more of HSDPA channels for a short transmission time interval of 2 milliseconds, significantly less than the interval of 10 to 20 milliseconds used in WCDMA. The network can thus readjust which users are assigned which HSDSCH every 2 milliseconds. REL 5 extended the R99 and REL 4 specifications offering the HSDPA enhancement and the IMS. The evolution of the UMTS technology continues with 3GPP REL 6 where significant uplink performance enhancements are achieved by introduction of high-speed uplink packet access, HSUPA, or responsive multimedia. HSUPA allows end users to effectively become the content provider. This will appeal to enterprise users and consumers alike. HSUPA is the incremental complement of HSDPA, delivering significantly improved data rates from the mobile back into the network with a theoretical peak data rate of 5.76 Mbps. HSUPA achieves its performance gains by upgrading various radio features of UMTS Release 5. Some of the major enhancements are: uplink scheduling mechanism is of central importance for HSUPA. The uplink scheduler, just as in HSDPA, is located in the node B. Task of the uplink scheduler is to control the uplink resources used by the UE in the cell. The scheduling mechanism is based on absolute and relative grants. The absolute grants are used to initialize the scheduling process and provide absolute transmit power ratios to the UE, whereas the relative grants are used for incremental up or downgrades of the allowed transmit power. Hybrid Automatic Repeat Request, HARQ, protocol is a retransmission protocol improving robustness against link adaptation errors. The node B can request retransmissions of erroneously received data packets and will send for each packet either an acknowledgement, ACK, or a negative acknowledgement, NAC, to the UE. Furthermore, the node B can do soft combining, that is, combine the retransmissions with the original transmissions in the receiver. Reduction of transmission time interval, to accelerate packet scheduling and reduce latency. HSUPA allows for a reduced transmission time interval, TTI, of 2 milliseconds corresponding to 3 time slots. A WCDMA radio frame of 10 milliseconds therefore consists of 5 subframes. Higher order modulation schemes, to increase downlink throughput without increasing bandwidth, higher order modulation schemes have been implemented. For instance, HSDPA employs 16 QAM. HSUPA uses BPSK or QPSK modulation, because these schemes exhibit lower peak-to-average signal ratios than 16 QAM. The mobile device's transmit capabilities are ultimately governed by their efficiency and limited battery capacity. The use of BPSK-QPSK with its lower peak-to-average signal ratio reduces demands on the mobile device. The resulting trade-off between efficiency and the end-user experience is a theoretical 5.76 Mbps peak data rate. HSUPA further enhances the HSDPA distributed architecture. Both the uplink scheduling and the HARQ protocol are located in the node B instead of RNC, in order to move processing closer to air interface and be able to react faster on the radio link situation. Node B contains a new medium access control entity called MAC-E, and the RNC contains a new medium access control entity called MAC-ES. Both MAC-E and MAC-ES entities terminate within the medium access control layer of the UE. Supporting high data rates and short TTI presents various constraints on mobile device design. More powerful processing and faster chipsets allowed to increase storage capabilities become prerequisites to handle the increasing amounts of data. With TTIs of 2 milliseconds, the mobile device must now react even faster to retransmission requests and control signaling from the network. Unlike HSDPA, however, the support of this 2 milliseconds TTI in the UE is not mandatory. Instead, it is a UE capability. It is configured at call setup, whether 2 milliseconds TTI or 10 milliseconds TTI is to be used for HSUPA transmission. Within the HSUPA framework, the Enhanced Dedicated Channel, EDCH, is introduced as a new transport channel for carrying user data on the uplink. On physical layer level, this translates into 2 new uplink channels. 1. EDCH Dedicated Physical Data Channel or EDPDCH carries the data load. 2. EDCH Dedicated Physical Control Channel or EDPCCH carries the pilot and power control channel information. The EDPCCH carries control information associated to the EDPDCH. In the downlink, 3 new channels are introduced for control purposes. 1. EDCH Absolute Grand Channel or EAGCH carries information that defines the precise characteristics of the mobile device's resource allocation. Absolute grants are used relatively infrequently as they contain a relatively large amount of information with a corresponding large downlink signaling overhead. 2. EDCH Relative Grant Channel or ERGCH carries relative grants. Information specified changes to a previous grant enabling optimization of resource allocation to each mobile device. This type of grant has a much lower signaling overhead. 3. EDCH Hybrid ARQ Indicator Channel or EHICH carries ACNAC to indicate the reception of data from node B to E. EAGCH is only transmitted from the serving cell. ERGCH and EHICH are transmitted from radio links that are part of the serving radio link set and from non-serving radio links. This completes the module. Click Next Topic from Navigation menu.